Kia ora and welcome to question 5 of the 2009 Scholl Calc exam. This question here is all about conics. First one here we've got a problem involving finding the eccentricity of an ellipse. The second one is a hyperbola. We're given the equation of a tangent to it, and we've got to show that the tangent only intersects the curve at one position. And then lastly we've got quite a challenging locus problem involving the intersection of two tangents forming a circle. Okay, so first up, part A, this ellipse here is drawn around a square so that the minor axis of the ellipse is the diagonal of the square, and the area of the ellipse is twice the area of the square. So you need to realize with this equation, the equation of the ellipse here in standard format, that this here is x equals a minus a, y equals b, and y equals minus b. That's when the axis goes right down the middle. Okay, so that means that the diagonal of the square is 2b, or not to be as they say in Shakespeare. We've got the relationship there, the area of an ellipse is pi times AB, and we need to use the fact that that area is double the area of the square. Okay, so if the diagonal of the square is 2b, that means that this length here is also b, based on the fact that the diagonals of the square will be the same length. And then we can use Pythagoras to find out that this here is root 2b, the side of the square. We got b squared plus b squared is 2b squared, square rooted is root 2b, or it's a 1, 1, root 2 triangle. Okay, so the area of the square is equal to root 2b all squared, or 2b squared. And then we're going to equate that to a half of pi AB. The area of the square is half the area of the ellipse. Let's put that all there. Finding the eccentricity of the ellipse. Eccentricity is a formula which is the ratio of C over A. If you didn't know, C, if we have an ellipse, it's a terrible one, but C is where the foci are and A is the vertex. The ellipse is a measure of how curvy it is. Sorry, eccentricity is a measure of how curvy the ellipse is, or how curvy a conic section is. And so if C is really, really close to A, then it will be quite a narrow ellipse. And if C is very, very far away from A, closer to the center, you basically get a circle. When C is equal to 0 right in the middle, you get a circle, and the eccentricity would be 0 in that case. Okay, so C over A is the ratio that we want. That's on the formula sheet, if you weren't sure. And then for an ellipse, there's a relationship between A, B, and C. If I draw this diagram here, this length is B. Again, apologies for the crappy ellipse. That's side C, and it turns out that this side here is A. The sum of distances from the foci to any point on the ellipse is equal to 2A. And if I consider the other half of this isosceles triangle I've just drawn, if the sum of the distances from the foci to a point on the ellipse is 2A, both those sides must be A. But again, if you didn't know that, there's a relationship on the formula sheet that tells you that C squared plus B squared equals A squared. But that's where it comes from, the definition of an ellipse. Okay, so eccentricity is equal to A squared minus B squared square rooted all over A. But we know that 2b squared is equal to pi over 2 times AB, cancelling a b from both sides. We've got, what am I going to do here? Let's get b in terms of A. So b is equal to pi over 4 times A. and then I can dump that into here. A squared minus pi squared over 16 times a squared all over a. There's a common factor of a squared underneath the square root. I can pull that out of the square root as an a and then cancel with the a in the denominator. So all the a's cancel and we're just left with the square root of 1 minus pi squared over 16. And if you work that out as a decimal, if you want to, you can work out that the eccentricity is a number that's less than 1, and it should be because c is smaller than a. It turns out to be 0.618, so 6193. Okay, the second question in this, we've got this hyperbola here, and we're given the equation for the tangent. Now, just have a look at the equation for the tangent and how it's so similar to the hyperbola. You can see there that the x squared, you take one of the x's for the tangent and the other one is a specific point x naught, and you take one of the y squareds, there is the y for the tangent and the other value is y naught. Everything else is the same. So that's quite a handy thing to memorize, because if you wanted to find that equation normally, what you would do is say y equals mx plus c is the equation of a tangent, substitute it into the hyperbola, and then solve a quadratic equation, make the discriminant equal to 0, and go about that process to find the equation. You might want to prove that this is the equation of a tangent. They've given you a specific point x naught, y naught, which means that you could use this form of a straight line and then just focus on finding the slope m in terms of a's and b's, but you don't need to because the question gives you that. Show that the tangent to the hyperbola at the point x naught, y naught does not intersect the curve anywhere else. Now, if you've got a hyperbola that looks like this, which is what an x squared minus y squared hyperbola looks like. This position here is a, this position is minus a, and we have a tangent at some point x naught, y naught. We could use a slope argument here and just say that the slope of that tangent is steeper than the asymptote of the hyperbola, because the hyperbola here has an asymptote that goes through, well, it should go through the origin. Let's correct that. Okay, it's got an asymptote here that has a slope m equals b over a. That's the slope of the asymptote there. And if the tangent is steeper, then it's not going to be able to go through and intersect the other branch of the hyperbola. That's what we're trying to prove. So I'll leave you to think about how you could use a tangent sort of slope argument there, and it mentions that in the schedule, in the assessment schedule as an alternative. But I think the question was intended to do it algebraically, so let's go about doing that. Okay, we've got the equation of the hyperbola, and we've got the equation of the tangent, and we solve this simultaneously and show that the discriminant equals 0. You can see that that second equation is a straight line because x naught and y naught are constants, so this is just some number times x and some number times y. It's a linear equation, and then substitute it into the other one, and I have a quadratic that I need to work with this discriminant. So it's going to get messy, but if I make y the subject of the second one, so there's my y, leave everything else alone, so move everything else away. Okay, we've got x naught over a squared minus 1 y times y naught over b squared times both sides by b squared over y naught, and that's my y equation. Then substitute it into the top, into the hyperbola. Oh, I can't wait to do this. We're squaring the y equation, and I've got a 1 over b squared as well. B to the 4 over y naught squared, x naught over a squared minus 1 all squared equals 1. Just wondering where my equation went. Okay, so that's a quadratic equation. We've got a 1 over a squared minus b squared over y naught squared times x naught squared over a squared times x squared. All I've done there is first I've simplified that constant as a b squared rather than b to the 4 over b squared, and I've expanded out the first part of that bracket, x naught squared a should be a to the 4, good thing I'm checking, and then all of that is the x squared term, and then the linear term is going to come from expanding that bracket, doing the sort of the cross terms. So there's two of those. It's a minus, so it's minus 2 lots of x times x naught over a squared times the constant that's in the front of the expression, minus b squared over y naught squared. That's the linear term, and then the constant term comes from the minus 1 all squared. So 1 times the constant that's in the front, minus 1 over b squared. Oh, no, I'd already simplified that. Minus b squared over y naught squared. Don't forget the 1 on the right hand side of the equation. It's also minus 1, and then equals 0. So that's a quadratic that's already in standard form. If you didn't like that, because I was kind of doing things in my head, expand the whole thing, rearrange it, and group the like terms together. We've got a couple of options here. We know that x naught, y naught, well, actually no, we don't. We know x equals x naught is a solution, because this is the tangent at the point x equals x naught, the tangent to the hyperbola. So what we need to prove is that this quadratic has a repeated solution, and that's the only solution. So I could use the sum and product of roots relationships here, and go sum of the roots is equal to minus b over a, not to be confused with the b and a from the ellipse, apologies, from the hyperbola. So that this dude here is the b part, and then this dude here is the a part, and I could work out what we've got here, or I could use the discriminant. So let's see which one's better. So minus b over a is 2 x naught over a squared times minus b squared over y naught squared, all over the a thing, which is 1 over a squared minus b squared over y naught squared times x naught squared over a to the 4. Gosh, what does that equal? I can times top and bottom by a squared to start. So that's going to be 2x naught times minus b squared. I'll also times by y naught squared while I'm at it. It's times by y naught squared at the top and a squared, top and bottom. Getting rid of fractions. So 2x naught times minus b squared all over 1, no, not 1, y naught squared minus b squared x naught squared all over a squared. Didn't get rid of all the fractions, it's annoying. Got some stuff here that doesn't look quite right. The fact that I've got a y naught squared but only an x naught on the top, why is that? One of the solutions is x naught here, and this is the sum of the roots. Okay, that might make sense as to why we've got that. So I've got to prove that x naught plus the other root, whatever it might be, it turns out it's going to be x naught as well. I've got to prove that this is equal to 2x naught. So the whole other thing should disappear, go to 0. No, not go to 0, go to 1. Oh, I know that x naught y naught is on the ellipse. I keep saying ellipse, I mean hyperbola. It's on the hyperbola. Therefore, this must be true. Okay, so how's that going to help? If I make y naught squared the subject of this equation, x naught squared over a squared minus 1 all times b squared, that's equal to y naught squared. If I then dump that into there, this whole thing, the sum of the roots is equal to 2 times x naught times minus b squared all over x naught squared over a squared minus 1 all times b squared minus b squared over a squared x naught squared. I hope some stuff cancels here. It does. The b squared over a squared x naught squareds cancel. And we're left with minus b squared on the bottom. The minus b squareds cancel. And we're left with 2x naught. The sum of the roots is equal to 2x naught. But one of the roots is x naught. So the other is x naught. That's the proof. Okay, if both of the roots to this quadratic, remember that this quadratic equation is giving us the points of intersection of the tangent with the hyperbola. And we know that one of the roots is x naught. If we've proven that the sum of the roots is 2x naught, it means it only intersects at x naught. It's a repeated root. Okay, now that wasn't too bad, but it had that little bit of insight at the end where we replaced the y naught squared expression. So I wonder if the discriminant would have been an easy way to do this problem. Go back to that quadratic that's in standard form, that's in yellow and blue at the top, and then I go straight to discriminant, b squared, okay, the b part, minus 4 times a times c. What a messy expression. X naught squared. 4 times a times c, which is that other random thing in there. There's a minus in both the terms for the c, so I'm going to change it to b squared plus 4ac and get rid of the minus there. B squared over y naught squared plus 1 equals 0. Okay, the discriminant. Well, actually, we don't know it equals 0. We've got to work out that the discriminant equals 0. Therefore, repeated root. It doesn't look like 0 at the moment. Okay, let's expand that first term. We've got 2, which squares to 4. X naught squared. B to the 4. A to the 4. Y naught to the 4. Be careful, it's a times in the middle there, so it's just one whole term squared. Plus 4. Okay, this one here is going to need some expanding. We've got 1 over a squared times that. B squared over a squared, y naught squared. We've got 1 over a squared. We've got minus b to the 4 x naught squared over a to the 4 y naught to the 4. And then the last term's minus b squared x naught squared over y naught squared a to the 4. Okie dokie. Are there any things that cancel straight off the bat? Yes, that term there cancels with that term there. Okay, and so we've got 4 b squared over a squared y naught squared plus 4 over a squared minus 4b squared x naught squared over y naught squared a to the 4. And I think we have to do the same thing as earlier. So we go back to the fact that we know that x naught y naught is on the hyperbola. And we replace the y naught squared stuff in that expression. 4b squared a squared x naught squared over a squared minus 1b squared. That's 4 over a squared minus 4b squared x naught squared over x naught squared over a squared minus 1b squared a to the 4. I'm sure stuff simplifies here, just can't quite see it. Let's cancel off the b squareds there, cancel b squareds there. We'll expand the brackets in the denominator. We've got 4 over x naught squared minus a squared minus 4x naught squared over x naught squared a squared minus a to the 4. See what we do with these fractions. 4 for x naught squared minus a squared plus 4 over a squared minus 4 x naught squared all over, let's factor out the a squared again. Okay, and then we can put these fractions together because they kind of have a common denominator. So we give the left fraction an a squared on top and an a squared on bottom. Now they are common denominators, and we give the middle term x naught squared minus a squared top and bottom. Now they're all common denominators, and we can put them all together. 4a squared plus 4x naught squared minus 4a squared minus 4x naught squared all over a squared x naught squared minus a squared. It's a lot of squaring. Cancel, 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 cancel equals 0. So the discriminant equals 0. X equals x naught is the only solution. The tangent only meets the hyperbola once. I actually preferred the sum of the roots method, if I'm honest. Okay, last question in the whole exam, probably a humdinger. Consider this ellipse. Hey, we're back to an ellipse, so I'll probably say hyperbola for the next 20 minutes. The point Q lies at the intersection of two perpendicular tangents. This time we're given the equation of the tangent in y equals mx plus c form. You can also prove it using discriminant stuff, or you could start with the equation of the tangent, which is this. It's exactly the same as the first part of part B, except we've got a plus. We don't need to prove this again. The question's hard enough. So given that this equation is the tangent to the ellipse with gradient m, we're told that the two perpendicular tangents, meaning that we can find the other tangent by taking the negative reciprocal gradient, show that the locus of Q is a circle. We can easily find the equation of this circle. It's actually quite a cool little thing. If I put the axis down there and then consider what happens when Q is there. When Q is at that position there, one of the tangents is vertical and the other tangent's horizontal, and this length here is A and this length here is B. So the radius of the circle is the square root of a squared plus b squared. So I could find the equation of the circle by saying x squared plus y squared is equal to a squared plus b squared. But that's not a proof. It doesn't prove it's a circle, it just gives us the equation of it by considering a trivial position. Okay, so what we need to do is find the point of intersection of these tangents. So if we have the first tangent is given to us, let's just consider the positive root, but it actually doesn't matter. Oh, we can put both in. Why not? We're going to be squaring, so it doesn't matter. And then the other tangent will be minus 1 over m there, and minus 1 over m in there. Same structure, just different slopes. And we need to find out where these intersect. To find out where they intersect, we want to solve a simultaneous equation, and then we want to prove that the simultaneous equation results in the circle equation I've just explained. There's different ways of solving simultaneous equations, like we could make these both equal to one another because they've both got the same subject. It turns out with this equation, if you rewrite them, because we need to square, I rewrite the first one like that by moving the mx term to the left. For the second term, second equation, I times everything by m, and then move the x term. So I'm going to get my plus x equals plus or minus m times, no, I'm not going to get that, I'm getting a squared over m squared. Okay, now rather than make y the subject, rather than equate them while y is the subject, I'm just going to square both sides right now. So that's giving me y squared minus 2mxy plus m squared x squared equals a squared m squared plus b squared. And then the bottom equation, m squared y squared plus 2myx plus x squared is equal to m squared times a squared over m squared plus b squared. The square root disappears. Just think about why I've done that and why it's useful. Simultaneous equations, there's different ways, like I was saying. You can use the elimination method now. If I eliminate, we actually don't want to find the point x and the point y, because then we're going to have to prove that they satisfy a circle equation. We don't need to find the x and y separately, we need to find what x squared plus y squared equals. So go back to the picture. The circle is centered at the origin, so we know that the left-hand side of this equation is going to be x squared plus y squared. That's what we want. We don't want x and y individually. Where if I had solved the simultaneous equation up here, I would have been finding x, and then I would have had to find y, and then I would have had to square them both and add them. So it just doesn't make sense to do it that way. Okay, if I look at these equations and I add them, adding them is going to cancel the cross terms, the x, y terms. So I'm going to get 1 plus m squared, lots of y squared. I'm going to get 1 plus m squared, lots of x squared. And I'm also going to get 1 plus m squared, lots of a squared plus b squared. Because that first term there is, actually no, it's not so obvious. This one here is equal to a squared plus m squared b squared. You can see that the a squared m squared and the a squared are on their own. So there's a 1 a squared and an m squared a squared. And there's also a b squared term and an m squared b squared term. So it's 1 plus m squared, all multiplied by a squared plus b squared. Divide through by that because it's never 0. I don't know where my equal sign went. Got carried away, got excited because it's such a nice simplification. And therefore we have the equation of a circle, which is a circle with a radius equal to the square root of a squared plus b squared. Center at the origin. And just to finish, I'm going to load up GeoGebra. And let's have a look at what we've just created. Okay, so what I've got here is the ellipse and the two perpendicular tangents. And if I change the slope, the tangents move. A and B are constants related to the ellipse. And you can see there that it's tracing out a circle.